So let us continue with our discussion on ideal transformer, which we started in our last lecture. And we told you that ideal transformers, to review that one, has got no resistance, no leakage flux, and that is no resistance. I'll quickly write so that you can recapitulate. No leakage flux. The value of permeability of the core material is quite large, that is mu r tending to infinity. And another point, I do not know whether I wrote or not, that is the core losses neglected. By core losses, I will take up those things in detail slightly, hysteresis plus eddy current losses. So, in a transformer having zero resistance and no leakage flux and having permeability of the core which is very large and core losses totally neglected, which core losses comprises of hysteresis and eddy current losses, we try to develop or analyze an ideal transformer. So, if you look at the basic thing, this we called it as core. This is the core, and the sides on which windings are wound are called limb, and this portion, horizontal portion, is called the yoke of the transformer. Anyway, what I told you, that the BH curve of a practical material will be somewhat like this, will be of this nature. Now, if you think the material of the core is replaced by better and better material, then the BH curve will go up and up, indicating that to establish a given amount of flux density or flux inside the core, you will be requiring lesser and lesser current. Okay. And the second thing we did also, that the applied voltage, the magnitude of which will be same as the induced voltage in the primary winding as well as in the secondary winding, and that is given by this root 2 pi f phi max into N1. So from this we told you that for a given applied voltage and given frequency, so you can write down for a given applied voltage and given frequency, the flux level inside the core of the transformer remains constant. Phi max gets fixed. No matter what is the material with which the core is made of. No matter what is the material of the core. This is very important thing. What is the material of the core? Material of core. Therefore, the assumption that, and this is so because the primary winding has to satisfy the KVL law. Applied voltage must be balanced by the induced voltage, that is N1 d phi dt should balance the applied voltage. From this really we get this particular information, and which can also be seen mathematically from this equation that phi max is nothing but V1 by root 2 pi f into N1. So other things remaining constant, V1 and f fixes the maximum value of flux in the core of the transformer. Now therefore you tell me that these are the different BH characteristics of different materials. So the moment you apply a fixed voltage V1 at a fixed frequency f, phi max value will be known to me for a given number of turns, that this much flux has been produced inside the core. So if phi max is known, I know the cross sectional area, I can calculate B max, and I want to know how much current it will draw from the supply at that time. So how shall I go about it? I will calculate phi max, then calculate B max, then I will fix up this B max here and try to read the current. Suppose this is the material which is presently used. Then I will say the current drawn from the supply, your ammeter will show this much reading. If you use this material, it will show this much of reading, and so on. Are you getting? So current drawn from the supply will change as you change the type of materials. Obviously, ammeter reading or the current drawn from the supply will go on decreasing if you use better and better material. Like this. Current drawn will be further reduced. So this assumption of the ideal transformer that mu r tends to infinity will therefore point to what? Suppose a material is used whose relative permeability is infinitely large, and you apply a given voltage and frequency, no current, I mean vanishingly small current it will draw to establish the flux. In the other extreme you think, suppose this material is totally replaced by air, no material is there, and it is replaced by air, or say by wood, this material is. Now the moment you apply a given voltage and frequency, the amount of flux to be produced inside the core is fixed, phi max. Now in air, to develop that phi max, you will require tremendous amount of current. It will draw very large current from the supply. Are you getting? Indicating that the inductance of the coil is very small. Therefore, if you can go on improving the material characteristics, that is BH characteristics of the material, you can easily show that the current drawn from the supply to establish a given flux inside the core of the material becomes lesser and lesser. So, in ideal situation, if I assume this mu are tending to infinity, it means that it will draw practically no current from the source. So under these circumstances, that is, in other words, this BH curve, I am assuming it to lie on the y-axis itself. That is, slope is infinitely large. Is not? This is the BH curve of the material in that very idealistic situation. Now, with this in mind, therefore, in an ideal transformer, once again I draw this one. This V1 is the applied voltage, and secondary is open circuited. I have not connected anything here. How the phasor diagram will look? Flux will be produced. So this is suppose the flux phi phasor. Of course, the current required to establish this flux is as small as possible, like this, small amount of current, or in that extreme situation, no current. So if that disturbs you, you always think mu r is very large and it draws very small current to establish this flux. Therefore, the applied voltage is here. Applied voltage is. So this small current or vanishingly zero current is required to establish this flux, and this is the applied voltage V1. And the induced voltages E1 and E2, they will be in V1 and E1 will be equal in length, and last time I showed this will be this one E1, and D2, depending upon the N2 value, it will be somewhere there. So this was the Phasor diagram of an ideal transformer under no load condition, and nothing to add to it, except that in this case, of course, this I developed last time, that E2 by V1 is nothing but N2 by N1. Another thing, in a transformer you should note that volt per turns remains constant in the primary and secondary side. It is the voltage per turn which remains constant. So this was there, and secondary there is no current as nothing is connected. It is like this. Now we will see what will happen if we connect a load across the secondary coil of the transformer. So under no load condition, this is the Phasor diagram of an ideal transformer. Okay. By loading, what I mean to say, suppose you have got a switch here and you connect some load, because after all you have changed the level of voltage to supply or to give appropriate voltage to the load. So under loading condition, what will happen to this ideal transformer, that we are going to study. So that is, when switch is closed, what happens? Okay. To do that, I need another information, that is, I will just refresh this one, that is called the dot convention of mutually coupled coil. Dot convention of a mutually coupled coil. Now for this I will not draw another figure, but refer to this diagram. Now you see that if you look at this diagram, I have drawn the winding showing its senses. That is how the winding is wound is very clear from the figure. Although in this figure I have just shown, one cannot really make out in which sense I have drawn this one in this simplified diagram. So first let us refer to this diagram here. Now let us assume that at any point of time this terminal is positive. Okay, current is entering through this terminal and it is positive, such that flux produced here is positive. The applied voltage as well as induced voltage changing with time, all the time, that is true. Let us consider an instant when this terminal is positive with respect to this one. So I have put a dot here. Now the question is, where should I put the dot at that point in the second coil, in the secondary? That is, we want to find out what will be the polarity of the induced voltage right at that instant when this terminal is positive. What will be the polarity of that voltage? Which one is positive? That one, if I can find out, I should put a dot there. Okay. Now how to do that? That is very simple to do, if you remember Lenge's law. Because of the fact this is the flux increasing with time. Now induced voltage polarity can have only two options, either this side plus, this side minus, right at that time, or this is minus, this is plus. Only two options are there. Let us assume, without bothering anything, just let us assume, suppose this becomes plus at that time, this becomes minus. Whether this is possible, let us first investigate that. Now we know that the polarity of the induced voltage should be such that it will try to oppose the cause for which it is due. Is not? That is what Lenge's law tells us. Now if flux is increasing there, at that time if I say this is the polarity of the induced voltage in the secondary, let us examine whether it opposes the cause for which this voltage has been induced or aids that cause. Now to understand this, you remember, I mean you think in this way. Suppose this voltage I allow to deliver power to some circuit. Suppose at that time you imagine some resistance I have connected, some load I have connected. this EMF, if the polarity is like this, in which direction it will deliver current to that load? This way. It is a source of battery now. It will deliver current like this. Current will come like this. Suppose this EMF polarity I have assumed, and let us imagine that this EMF will now act in some circuit. So right at that moment, the current will come out from this terminal and go to the load, come back here and flow like this. This way it will flow. Okay. Now secondary coil carries current. What will be the direction of the flux produced by it? I will apply that rule here, and it will be produced in this way. So what is the thing now? It aids the cause for which the voltage has been induced, which is not possible. That is, the polarity of the induced voltage of the secondary terminal should be such that it should oppose the cause. What was the cause? Cause was flux was increasing in this direction. Now, if for argument's sake, let us assume this is plus, this is minus, then this EMF, if it is allowed to act in an external circuit, then it will create a flux which will further aid that cause, which is negating the Lenz's law, which is not possible. Let us see the other possibility then. Suppose let us assume this becomes plus, this becomes minus. In that case, this EMF, suppose this is assumed to be plus, this is minus at that instant, then in that case, if this EMF is allowed to act in an external circuit by connecting a load, it will try to pass current in this way and load, it will come out here, and then in the winding it will flow like this. And the flux produced by the secondary coil will try to oppose this increment in the flux produced by the primary. Therefore, this is the correct polarity at that time. So, if you have put a dot, I can put a dot here. I will draw it rather neatly and tell you once again what I mean by this one, and I will draw rather several coils in order to ascertain the polarity of mutually coupled coils. Suppose you have a coil like this. You have a coil like this. And suppose you have got another coil, just like this. And in each of the coils, I know the sense of the winding. Really, I know. Now, suppose I put a dot here. For this coil, where the dot will be? Top one. Tell me for this one, where the dot will be? This one or that one? This side will be dot. Let us assume this will be dot with respect to this one. If you energized, then it will drive current here. It will go like this. It will go like this, and it will aid that original flux, which is not possible. In fact, this side. Okay. Therefore, given the windings actual sense, without doing any experiment or things like that, we can ascertain just by this argument where the mutual coupled dots will be there. Obviously, if you put dots here, other three terminals are also dot, the other left out pairs. Dot means the polarity of the voltages at any point of time. This dot also means when this will be negative, all these terminals will be negative. So other terminals also then will have same kind of polarities at a given time. So I have shown it by square. So showing one dots is sufficient. Of course, this is overemphasized. Are you getting? This way I can connect. So this is the dot convention which will be followed. Now, in fact, that is the reason when you draw a simplified diagram to represent a transformer, you are not going to show the core of the transformer, etc. How will you show in the simplified diagram some coil like this, another coil like this? and the core is represented by a few lines drawn here. That core, symbolically it is shown there. But here, given this type of diagrams, you cannot make out which one is dot, which one is cross. The winding really has gone this way or that way. It is just a sort of quick diagram. So here, dot should be specified. For example, if you are given a transformer, suppose you are given a transformer. In transformers, what happens is this: two terminals from primary winding comes out and reach you from the top box as two terminals, and two terminals come out from the secondary of the transformer, and you don't have any way to look at the sense of the winding. Suppose if you could see is opening it all together, seeing the winding is moving like this, then no test is required. You can tell this is dot like this argument. But that is not possible in a practical transformer. What is available to you? The two terminals for primary, two terminals for secondary, like that. So how to know the dots of a given transformer? So what I will do is this. Suppose I can do like this by two ways. So this is how to know the dots of a given transformer. So for this, of course, you have to do some testing or some tricks here. So what you do, suppose the transformer is given, I do not know where the dots are. Of course, you are free to choose one dot of a coil. That I can start with. Suppose this is positive at a point. Which one is positive, I want to know. What I will do is this. I will apply a voltage here, AC voltage, say V1, I will apply. Rated voltage of this winding. I know how much. Suppose it is a 200 stroke 100 volt transformer. Suppose. So this side I will apply 200 volt. How much voltage will be induced? Suppose you take a voltmeter, moving iron, connect it here. How much will be in the induced voltage? 100 volt will be induced. That is, turns ratio is 2:1. So you apply a known voltage. Now you take another voltmeter. You take another voltmeter. Take two wires. Connect one here and another there. How much will be the reading of the voltmeter? No, it will be 0, because where is the closed path? Right now, up to the point I have drawn, it will not read anything. Because potential always between 2 points. You should start from one point, reach the other. Right now, it will not read anything. Now suppose, but these 2 points are joined. Then this voltmeter reading will be this voltage and this voltage. It will come like this. Now, if this is also suppose dot, I do not know which one is dot. Suppose this is dot. Then you have applied 200 here. Here RMS voltage will be 100 volt, no doubt. This dot, if it is suppose like this, then that means you start from 1 plus, then this is minus, and once again minus plus. So difference will be read by the voltmeter. So if the voltmeter reads, if V reading is 100 volt, then this is correct. Then the dots here I will draw. Dot should be like this. If V reads 300 volt, then the dots will be like this. You have assumed this to be dot, this is dot. That is, in that case, this will be plus, I mean, you cross it out, this is suppose dot. So you can easily see you start from this one minus 2 plus, then once again minus 2 plus, as if two batteries are connected in series with minus plus minus plus. So you will be getting twice this voltage. So one way of knowing the polarities by doing simple test like this. Okay. But only since I am telling about this, I finish it in this by saying this. This method is correct, very nice. But if the voltage ratio is pretty large, this method may not give you a very accurate reading. I mean, you just think of a transformer, suppose, whose rating is 6000 volt by 100 volt. Okay. I connect the transformer like this. So I will apply say 6000 volt here, or rather 100 volt in lab, say 100 volt I will apply on this side. 6000 volt will be induced here. And if you connect like this, what will be the possible readings of the voltmeter? 6100, 5900. So your voltmeter may not distinguish these two. That is, two numbers you are adding and subtracting. If one number is very small compared to the other, the difference in the two readings may be deceptive. Who is doing the experiment or trying to identifying the polarity of a transformer. So this is okay, fine if the level of voltage is rather high. So in that case, what is done? Another method is there in such very peculiar cases when the voltage ratios are quite large. In that case, what they do is DC kick test can be incorporated. What you do here, you take the transformer. Instead of applying AC, what you do, you have a suppose some DC source, and connect it with a switch. Your class 12 experiment or introducing Faraday's law, and you connect a zero-centered voltmeter here. This is zero-centered voltmeter. Zero-centered voltmeter. Okay, and this is suppose plus minus of the battery. You take a small battery. You close the switch. The moment you close it, there will be induced voltage. Although DC, but there was no flux. Now flux will be established. There will be some d phi dt. Of course, there will be a voltage pulse generated on the secondary side. What will be the polarity of this voltage? Suppose this voltmeter gives positive reading, means that this side is plus. Suppose plus of the voltmeter you have connected here. So, but I know from this one that I have applied this side plus voltage. That is, if this is dot, if it gives positive reading, this will be also dot. Okay. Otherwise, if it gives negative here, this should be dot. I think this is very straightforward thing. So this is called DC kick test in such cases. Anyway, so this polarity thing is important to understand the performance of a transformer when it is loaded. So now let us understand the loading of ideal transformer. That is, this one is there, your transformer, and this is your primary winding, and suppose the sense of the winding is also known. I am drawing it like this, and I have a switch here and a load. And here I have applied steady state AC voltage, say V1 bar, and induced voltage will be there U1, E2. Okay. And since it is an ideal transformer, prior to loading, this was the situation. This was the applied voltage. Yes, there was flux decided by supply frequency and the applied voltage. But the current drawn was very small, because I have assumed its permeability is very large. That is, if you connect an ammeter here, it will read no current, and it should not disturb anybody. That is what I want to tell. Okay? Because of our assumption, I have assumed very good magnetic material, which requires vanishingly small current. So some current was there. It was like this. And in the secondary, I have got both E1 here, and suppose it is a step up or step down transformer. Depending upon that, this E2 length will be decided. I think that is clear to you. This E2 is there. Obviously, this one dot is known to me either by going through the sense of the winding or by doing some test. These dots are known. Now let us imagine this switch is closed. That is, I want to draw power from the secondary of the transformer. This impedance I have connected some Z2 bar. So some current will flow. Let us call it as I2 bar on the secondary side. Okay. Where will be the Phasor I2 bar? It will be decided by the power factor angle of Z2 bar, and with respect to E2 it will go. Suppose let us assume some lagging current, lagging power factor load I2 bar. It will lag E2 by some power factor angle theta 2. But now what happens? This you should understand. The moment the transformer is loaded on the secondary side, so long the flux developed prior to the closing of the switch, when the transformer was under no load condition, the flux developed in the core was solely decided by the MMF produced by the primary winding, this N1 into that vanishingly small current. That was the MMF which was acting in the circuit, and that created this flux. Now the moment I load it, secondary winding carries current. What is the total, and I want to find out the flux. What is the total MMF now acting in the circuit? The secondary MMF as well as primary MMF. What was there vanishingly small like this. And also you note that the secondary MMF direction will be in the opposite direction. I2 like this, it will go in the opposite direction. So what will happen? The flux level in the core will get upset. What it was earlier, phi max, it will change. Is not? But how it can change? Because in the primary circuit, one should not forget the KVL law is to be satisfied. Applied voltage should be equal to d phi dt, no matter what you are doing on the secondary circuit, doing this, that, opening, closing, whatever you do here, the flux level in the core is to be this one, decided by this phi max, decided by V1 by root 2 pi Fn1. It has nothing to do with what you are doing there. The KVL law in the primary is to be satisfied. Therefore, the moment the secondary is loaded, secondary is drawing some current, the total MMF acting in the circuit gets upset, and phi max is to remain constant once again. How it can happen? It can happen only this way. If the secondary carries I2 current, the moment you load it, primary 2 will draw now extra current, such that the N1 into I1 will be equal to N2 into I2. I will repeat this point. What I mean to say, that suppose this was the primary winding. This is very important and interesting also. See, earlier there was no secondary current. to produce phi max, how much MMF you require? That is already known to me. That is equal to N1 into IM, this small current, which is very small. Are you getting? That MMF was acting alone and it produced phi max. Now the material is fixed. After loading also phi max is to be established in the core. So what is the total net MMF required? Once again, see, in a magnetic circuit now two coils are there. But net MMF acting in the circuit will decide the level of flux to which it will build up. Now what I am trying to tell, this flux level under no load condition and flux level during loaded condition, it should not change. Because of what? Because primary KVL is to be satisfied. Applied voltage is N d phi dt. It is decided by this one. So now, when it was not loaded, whatever MMF was necessary, which was vanishingly small, that Im was vanishingly small into N1, that MMF, resultant MMF should be also this one when you have loaded the transformer. What I am trying to tell. Suppose the MMF necessary during no load condition was, to put it numerically, suppose 1 ampere turns, it was necessary. I mean, some figure I am trying to tell. You have loaded the transformer. Something load current is supplied to the secondary, this, that happened. But what I am trying to tell, after you have loaded the transformer, the total MMF acting in the circuit should be finally 1 ampere turns. Are you getting? But once you have loaded this transformer, secondary is carrying a current I2. What is the MMF developed by the secondary? N2 I2. So there must appear another MMF in the transformer which will fully cancel out the effect of N2 I2, such that what MMF remains in the circuit? The earlier one. Okay. I mean, to tell you, slightly I will digress from this ideal transformer. Let us put it also in this way. Suppose it is not so ideal a transformer. I am slightly digressing from ideal transformer in this sense, so that those problems do not remain in your minds. Suppose it was a finite permeability, so it was drawing some IM, magnetizing current, under no load condition, and it developed a flux phi. There was induced voltage in the primary, I mean, whose length E1 is same as V1, this is, and there was a secondary voltage E2. Under no load condition, what was the MMF acting in the circuit? N1 into Im, and it established this flux phi. What I am trying to tell, if you load the transformer, let secondary carry current, let primary carry extra current or not, I do not know, some currents let it carry. But the net MMF acting in the circuit should be how much? N1 into Im. Now what I am telling, this is I2, secondary current is suppose I2, here I2. So what is the secondary MMF? N2 I2. So primary should draw now extra current to balance it out, such that is on the top of Im it will draw extra current. Im will be there in the circuit, it will draw. Now how it can do so? You see, suppose what will be the phase relationship of this current and the current drawn, extra current drawn from the supply? Suppose this is I2 here. In which direction should you think that the primary will draw current from the supply? This way or the other way? So that the MMF will be nullified. So if it flows like this, the secondary will try to produce flux in this direction. Secondary will try to produce flux in this direction. Primary will draw extra current from the supply in this direction, such that these two fluxes will be cancelled out. That is, in this diagram, if I show it, it should be like this. I2 will be there. So I2 and I1 will be in time phase. Let I2 go on increasing, I1 will also increase. Let I2 come to 0, I1 means the reflected current on the secondary on the primary because of the secondary current. So this is shown in the phasor diagram in this way. Suppose this is I2. Now primary will draw extra current, I2 dashed, whose magnitude will be I2 by A. That is N2 I2 by N1. That is, the additional current primary will draw, the magnitude of which should be such that I2 dash N1 will be equal to I2 N2. So under loaded condition, what will be your ammeter reading? When you have loaded, this IM is there. IM plus this I2 dashed. IM plus this I2 dashed. That is, the MMF acting in the circuit should remain same whether you have loaded the transformer or not. Because of what? Because flux level in the core does not change with loading. It has to remain constant. Because of what? Because it has to satisfy the KVL equation on the primary side. The flux level gets decided by supply voltage frequency. Flux level is fixed, no matter what you are doing on the secondary side of the transformer. So this IM I brought in, but let me go to that ideal transformer. Suppose now the transformer is ideal. Then in that case, what will happen? This is V1 voltage. IM is now vanishingly small, 0. Phi is there. This is the flux phasor. Your induced voltage phasor will be E1 and E2 will be there. Primary current drawn from the supply is now 0 because of this idealistic situation. IM I have assumed 0. In ideal transformer phasor diagram. This is the ideal transformer phasor diagram. No load condition, this is there. IM is 0. Now you load the secondary, that is you close this switch in this ideal transformer. So on the secondary side there will be a current I2 at a power factor angle theta 2. And what will be the primary current drawn? That initial 0 current, to this I have to add I2 dash. Now it is 0, that's why it will be just like this. On the same line you extend this I will call I2 dashed, and this will be equal to I2 by A, where A is the turns ratio of the transformer I last time defined. Therefore, if one goes through the reading of the ammeter, when the switch was closed it was 0. If you close the switch, you will find this ammeter now reads. And apart from all this physical reasoning, this of course should be like this only, because the moment you try to derive power from the secondary coil of the transformer, who is the only source of power input to this system? This one. Its current must rise, otherwise how it can deliver power to your secondary? That is the one, very simple explanation to all these things. That is okay, you have connected a load on the secondary side, it delivers power. Forget about direction of flux, etc. Output power is there. But this is the only source of power. So it must now pump power into the primary. The moment you want to drop power out of the secondary, power will be automatically pumped in. Of course, you need not bother about that. Let the primary now starts drawing power from the supply like this. it will be automatically done. You need not worry about this. So with this ideal transformer, therefore, we find this relation is true. And this I2 dashed will be actually the ammeter reading here. So this relation, apart from this voltage relation that we got in our earlier class, that is the voltage per turn remains constant V1 by N1, or rather E1 by N1 is equal to E2 by N2. This was the voltage equation we have got. Now we get another important relationship, that is the I2 dashed into N1 is equal to I2 N2. What is I2? I2 is the actual secondary current. What is I2 dashed? I have put also I2 here and put a dashed to indicate that it is an current drawn by the primary because secondary is carrying a current. So that's why I2 dashed I have written, to show that on its own it will not draw current from the supply. So it is called reflected current in the primary, reflected current in primary. So I will stop today and conclude this one very quickly. What I have done today, that I have first considered that ideal transformer like this. Don't talk, hello. So I have considered an ideal transformer and showed you what will be the phasor diagram of the ideal transformer, and then I have developed the thing that when the secondary of the transformer is loaded, how primary will respond to that. Okay, thank you.